Hi guys, welcome to my channel, Nerd Talk. I am excited to share this video with you all, so be seated and get ready for second tour. This is part 2 of our journey through the formation of the universe and the solar system. In this episode, we dive deeper into Earth, the life-sustaining world we call home, Moon, our constant companion, who is by our side always. Let's recap. In part 1, we journeyed back to the beginning, about 13.8 billion years ago, when the Big Bang gave rise to space, time, and energy. As the universe expanded and cooled, the first elements, hydrogen and helium, formed. Under the pull of gravity, they came together to create stars and galaxies. Inside these stars, heavier elements were forged, and later scattered across space through powerful explosions, becoming the building blocks of future planets. Around 4.6 billion years ago, within the Milky Way, a massive cloud of gas and dust collapsed to form the Sun at its center, surrounded by a spinning disk. From this disk, particles gradually came together to form planets. Closer to the Sun, only rocky worlds could form Mercury, a small, cratered planet with extreme temperatures, and Venus, which developed a thick carbon dioxide atmosphere, making it the hottest planet in the solar system. Today, we turn our attention to Earth, the third planet from the Sun, a unique world where the conditions for life came together. Building Earth, from dust to a fiery world. Imagine the early solar system not as calm and empty, but as a chaotic, swirling cloud around the young Sun. Inside this rotating disk, tiny specks of dust began sticking together due to electrostatic forces, almost like cosmic static electricity. These particles slowly grew into grains, then pebbles, and eventually solid rocks. As time passed, these rocks collided again and again, forming larger bodies called planetesimals, small, asteroid-like objects racing through space at high speeds. The process wasn't gentle. Some collisions shattered objects, but many caused them to merge and grow bigger. In one region of this disk, a particular mass began to dominate, pulling in more and more material due to its increasing gravity. This growing body became the early version of Earth, known as Proto-Earth. But this was no peaceful planet. It was a blazing, violent world. Every collision released massive energy, heating the surface until it melted completely. Earth became a glowing sphere of molten rock, constantly bombarded and reshaped, a true fireball in space. This intense beginning set the stage for everything that followed, from the formation of the Moon to the development of oceans, atmosphere, and eventually, life itself. As Proto-Earth remained molten, gravity began sorting its materials by density in a process known as differentiation. Heavier elements like iron and nickel sank to the center, forming a dense core, while lighter silicate materials rose to create the mantle and crust. This process built the layered structure Earth still has today, a solid inner core, a liquid outer core that generates Earth's magnetic field, a thick mantle of slowly flowing rock, and a thin, fragile crust on the surface. From a chaotic molten mass, Earth transformed into a structured and dynamic planet. One of the most dramatic events in the early history of Earth was the giant impact hypothesis, a colossal collision with a Mars-sized protoplanet called Theia. The impact was so intense that it blasted vast amounts of debris from Earth's outer layers into space, forming a glowing ring around the planet. Over time, this material came together under gravity to form the Moon. This event not only created the Moon, but also shaped Earth's tilt and rotation, helping stabilize its climate over billions of years. After the moon-forming impact, Earth remained an extremely hostile world. Its surface was largely molten, and its atmosphere was thick, with volcanic gases such as carbon dioxide, methane, ammonia, and water vapor completely lacking oxygen. Intense volcanic activity released gases from deep within the planet in a process known as outgassing, gradually forming a primitive atmosphere. The young Earth was a world of fire, extreme heat, and constant geological activity far too harsh to support life. First atmosphere, which was lost to space. After Earth formed about 4.5 billion years ago, it initially had a light atmosphere composed mainly of hydrogen and helium, the most abundant gases in the early solar system. However, this atmosphere was not stable. Due to Earth's relatively weak gravity at the time and strong solar winds from the young Sun, these light gases gradually escaped into space. As a result, Earth completely lost its first atmosphere, leaving the planet exposed and leading to the formation of a new, more stable atmosphere later. Next, let's explore the Moon. The Moon is Earth's only natural satellite and one of the most prominent objects in the night sky. Formed about 4.5 billion years ago, it orbits Earth at an average distance of around 384,400 kilometers. Though it appears bright, the Moon does not produce its own light, but reflects sunlight from the Sun. Its surface is rocky and heavily cratered, making it a fascinating subject of study and exploration throughout human history. How the Moon shaped Earth. The Moon has played a crucial role in shaping Earth's environment and making it suitable for life. One of its most important effects is stabilizing Earth's axial tilt. Without the moon, Earth's tilt could vary wildly over time due to gravitational influences from other planets, leading to extreme and unpredictable climate changes. Because the moon acts like a stabilizer, Earth maintains a relatively steady tilt of about 23.5 degrees, which results in regular and predictable seasons. The moon's gravitational pull also creates ocean tides. These tides cause the continuous movement of water along coastlines, which in early Earth helped mix chemicals in the oceans. This mixing is believed to have played an important role in the development of early life by bringing nutrients together and creating dynamic environments where complex molecules could form. In addition, the moon has gradually slowed down Earth's rotation over billions of years through tidal friction. In the early days, Earth spun much faster, and a day may have lasted only a few hours. The gravitational interaction between Earth and the moon caused energy loss, which slowed the rotation, eventually leading to the 24-hour day we experience today. Overall, the moon is not just a companion to Earth. It has been a key factor in maintaining a stable climate, supporting ocean processes, and shaping the conditions necessary for life to develop and thrive. Moon. In the silent world, the moon may look like a quiet, lifeless rock in the sky, but inside, it tells a story of fire and transformation. Billions of years ago, the moon was completely molten, a glowing sphere of melted rock. As it slowly cooled, heavy elements like iron sank to the center, forming a dense core, while lighter materials floated upward, creating layers, just like oil separating from water. At its center lies a surprisingly small core, made mostly of iron, mixed with nickel and sulfur. Surrounding it is the mantle, a thick layer of solid rock, but not entirely dead. Some parts may still be slightly molten, which is why the moon experiences subtle tremors called moonquakes. The outermost layer, the crust, is where things get visually interesting. It's uneven, thinner on the side facing Earth, and thicker on the far side. The bright regions you see from Earth are ancient highlands, while the dark patches, called Maria, are actually old lava plains formed when molten rock once flooded the surface. On top of all this lies the regolith, a blanket of fine dust and broken rock, created by billions of years of meteorite impacts. It's not like Earth's soil, it's sharp, dry, and untouched by wind or water. Beneath it is an even more shattered layer called the megaregolith, showing just how heavily the moon has been bombarded over time. What's wild is that scientists didn't just guess all this. We actually confirmed it using rock samples brought back by the Apollo program, along with modern tech like seismic studies and satellite analysis. So yeah, the moon might look calm and frozen in time, but inside, it carries the memory of a violent, fiery past. Now we will discuss about the atmosphere of the moon. So basically the moon doesn't really have an atmosphere like Earth. Instead, it has something called an exosphere, which is so thin it's almost like a vacuum. Imagine standing on the moon. There's no air to breathe, no wind, no sky as we know it, just endless space. The particles present, like helium, neon, and argon, are so far apart that they almost never collide, making the atmosphere extremely weak and barely noticeable. But here's the cool part. This exosphere is not stable at all. It's constantly being created and lost. Tiny micrometeorites hitting the moon's surface, and streams of charged particles from the sun knock atoms off the surface and send them floating into space. Some of these particles escape forever, while others fall back down, creating a kind of slow, invisible cycle. So unlike Earth's thick, protective atmosphere, the moon's atmosphere is more like a temporary ghost, always forming, always disappearing, and constantly changing. Imagine a massive space rock hurtling through space at incredible speed, and then, boom, it crashes into the surface of a world with unimaginable force. In that single moment, energy explodes outward, rock melts, debris flies in all directions, and a giant scar is left behind. That scar is called a crater, a circular, bowl-shaped depression formed when an asteroid, meteoroid, or comet strikes a planet or moon. Now, when we look at lunar craters on the moon, we're not just seeing random holes. We're looking at a perfectly preserved record of billions of years of cosmic impacts. Unlike Earth, the moon has no atmosphere, no water, and no geological activity. So once a crater forms, it stays there, almost unchanged. These craters were created by continuous collisions from leftover material in regions like the asteroid belt, Kuiper belt, and Oort cloud. Craters come in different types depending on their size and the energy of impact. Simple craters are small and bowl-shaped. Complex craters are larger and develop central peaks and terraced walls due to the collapse of the surface. The largest impacts create basins, enormous craters over 300 kilometers wide. Many of these formed during the late heavy bombardment and were later filled with molten lava, forming the dark plains called Maria visible from Earth. The formation of a crater happens in two stages. First is excavation, where the impact blasts out a deep cavity and throws debris outward. Second is modification, where the surface rebounds and collapses, forming peaks, terraces, and a wider structure. In extremely powerful impacts, the rock behaves almost like a liquid, before cooling into fractured material called lunar breccia. In the case of massive impacts forming basins, entire regions of the moon's crust melt, creating rings, cracks, and deep structures. Magma later rises to fill these large depressions, and slowly cools over millions of years, forming the dark regions we see today. So when you look at the moon, you're not just seeing a glowing object, you're seeing the scars of ancient cosmic explosions, frozen in time. Impacts cause rocks to be compressed, melted, and ejected, forming patterns and secondary craters. These features provide valuable insights into the processes that shape the moon and the entire solar system. Look up at the sky for a few nights, and you'll notice something magical. The moon is constantly changing its shape. But here's the twist. The moon isn't actually changing. We are just seeing different portions of its sunlit side as it orbits Earth. This cycle, called the lunar phase cycle, takes about 29.5 days and follows a beautiful, repeating sequence. It all begins with the new moon, when the moon is positioned between Earth and the sun. The side facing us is completely dark, so the moon is basically invisible in the sky. As the moon moves forward in its orbit, a tiny sliver of light appears. This is the waxing crescent, where a thin curved shape becomes visible and grows a little brighter each day. Next comes the first quarter, where we see half of the moon illuminated, even though it's actually a quarter of the total moon. It rises around noon and is clearly visible in the evening sky. After this, the moon enters the waxing gibbous phase, where more than half of it is lit up, and it continues to grow brighter night by night. Then we reach the full moon, when Earth lies between the sun and the moon. The entire face of the moon is illuminated, making it appear fully bright in the night sky. It rises at sunset and sets at sunrise. This is the phase most people recognize instantly. After the full phase, the moon begins to shrink in brightness. This is the waning gibbous phase, where the illuminated portion starts decreasing. Then comes the last quarter, where again half of the moon is visible, but now it rises around midnight and is seen mostly in the early morning. Finally, the moon becomes a waning crescent, a thin, fading curve of light just before sunrise. As it continues its orbit, it returns back to the new moon, and the entire cycle repeats. So the phases of the moon are not random. They are a smooth, predictable dance between the moon, Earth, and the sun. Every night, you're watching a different chapter of the same cosmic story unfold in the sky. The moon is tidally locked with Earth, so we always see the same side. A slight wobble, called libration, allows us to see slightly more than half of its surface over time. During crescent phases, a faint glow called earthshine is visible, caused by sunlight reflecting from Earth onto the moon. The moon, a story of fire, ice, and discovery. Imagine the early Earth as a fiery, chaotic world, and then suddenly, a massive collision changes everything forever. Around 4.5 billion years ago, a Mars-sized object called Theia crashed into the young Earth with unimaginable force. This violent impact blasted huge amounts of molten and vaporized rock into space, forming a glowing cloud of debris. Over time, gravity pulled this material together, and it cooled and combined to form the moon. This process is explained by the giant impact theory, the most widely accepted explanation for the moon's origin. After the collision, the debris formed a ring around Earth, and gradually, this material came together to create the moon. In its early stages, the moon was extremely hot and likely covered by a global ocean of magma, which slowly cooled and solidified to form its surface. For many years, scientists believed the moon was completely dry, but modern discoveries have revealed that small amounts of water do exist. This water is mainly found as ice, trapped in permanently shadowed craters near the poles, and as tiny molecules locked within lunar rocks. Although the moon remains extremely dry compared to Earth, this discovery is significant, especially for future exploration. Even today, scientists continue to study the moon to uncover its secrets. Missions and programs like the Artemis program aim to send humans back to the moon and bring back new samples. These efforts will help us better understand how the moon formed, how it evolved over billions of years, and how it may support future space exploration. Imagine looking up at the night sky for thousands of years, seeing that glowing moon, and wondering, what's it really like up there? Now imagine the moment humanity finally stopped wondering and actually went. On July 20th, 1969, during the historic Apollo 11 moon landing, that dream became reality. As the world held its breath, Neil Armstrong stepped onto an alien world and delivered a line that would echo through history. One small step for a man, one giant leap for mankind. In that instant, the moon was no longer just a distant object in the sky. It became a place humans had touched. That single step wasn't just about reaching the moon. It was proof that human curiosity, courage, and determination could push beyond limits we once thought impossible. Imagine standing on Earth billions of years ago. Not the blue planet we know today, but a blazing, chaotic world of fire and destruction. The ground beneath you would be cracked and glowing, volcanoes erupting endlessly, lightning tearing through a thick, toxic sky, and from above, fiery space rocks crashing down like cosmic missiles. it looked less like a planet, and more like survival mode turned to maximum. But hidden inside this chaos was the beginning of something extraordinary. As Earth slowly began to cool over millions of years, a major transformation started in the atmosphere. The thick clouds of water vapor, released earlier by intense volcanic activity, began to condense. And then came something almost unimaginable. It started to rain. Not just for days or years, but for millions of years. Endless rainfall poured onto the hot surface, hissing as it hit molten rock, gradually collecting in low-lying regions. Drop by drop, basin by basin, the first oceans of Earth were born. At the same time, Earth wasn't building its water supply alone. Space itself joined the process. Countless meteoroids and comets, especially water-rich ones like carbonaceous chondrites, collided with the planet. These weren't just destructive impacts, they were deliveries. They brought additional water locked in minerals and ice, adding to the growing oceans. So while volcanoes were releasing water from inside Earth, space rocks were delivering water from outside. A perfect combination. This double source, internal outgassing and extraterrestrial delivery, completely transformed Earth. What started as a dry, molten world slowly evolved into a planet, covered with vast life-supporting oceans. And here's the coolest part. This wasn't just about water filling holes. These oceans became the foundation for everything that came later. Without this phase, there would be no chemistry turning into biology, no life, no evolution, basically, no us. So yeah, Earth didn't just get oceans, it earned them through fire, rain, and cosmic chaos. Picture Earth at a time when the ground itself was breathing fire. Massive volcanoes erupted non-stop, tearing open the surface and releasing enormous clouds of gas into the sky. This wasn't just destruction, it was construction. This phase, known as volcanic outgassing, built Earth's second atmosphere. Because the young Earth was still extremely hot and molten, gases trapped deep inside the planet were constantly escaping through volcanic eruptions. Over time, these gases accumulated and formed a thick, heavy atmosphere. It was made mainly of carbon dioxide, water vapor, hydrogen oxide, and nitrogen, N2, along with smaller amounts of methane, carbon tetrahydride, and ammonia, nitrogen trihydride. The sky would have looked dark, hazy, and hostile, nothing like the clear blue we see today. And here's the key detail. There was almost no oxygen. That means this atmosphere was completely toxic and unbreathable for modern life. But at the same time, it was perfect for setting the stage for what came next. The water vapor in this atmosphere would later condense to form oceans, and the gases present would fuel the chemical reactions that eventually led to the origin of life. So even though it looked deadly, this volcanic atmosphere was actually Earth's way of preparing itself for life in the future. After millions of years of intense rainfall, the oceans had formed, and with them came stability for the very first time in Earth's history. The once molten surface slowly cooled and hardened, forming a solid crust over the planet. What was once a fiery ocean of lava was now turning into actual land. At the same time, something incredibly important began: the early water cycle. Water from the oceans started evaporating due to heat, forming clouds, and then falling back again as rain. This continuous cycle of evaporation and condensation helped regulate the planet's temperature, preventing extreme fluctuations. The oceans played a major role here. They acted like a giant heat absorber, stabilizing Earth's climate and creating more balanced conditions. And this is where things get really interesting. For the first time ever, Earth had everything needed for life to begin: liquid water, a stable surface, and a chemically active environment full of reactions waiting to happen. Basically, Earth had gone from a burning hellscape to a planet quietly preparing for life's grand entry. As the planet continued to cool, a dramatic transformation began in the atmosphere. The thick clouds of water vapor that once filled the sky started to condense into liquid water. And then came one of the most intense events in Earth's history: endless rainfall. This wasn't ordinary rain. It poured continuously for millions of years, falling onto the hot surface and slowly collecting in low-lying regions. Gradually, these accumulating waters gave birth to the first oceans. What was once a dry, volcanic world began turning blue. But something equally important was happening at the same time. Carbon dioxide, which dominated the atmosphere, started dissolving into these newly formed oceans. It reacted with minerals and formed carbonate rocks, effectively removing carbon dioxide from the atmosphere. This process was a game changer. By reducing carbon dioxide levels, it helped cool the planet further and stabilize Earth's climate. The oceans didn't just form, they became powerful regulators of temperature and chemistry. So this third atmosphere phase wasn't just about rain and water, it was about transformation. Earth was shifting from a harsh, unstable world into a more balanced, life-friendly planet, quietly setting the stage for the origin of life. Around 3.8 billion years ago, simple chemical compounds in Earth's oceans began interacting. Energy from lightning and hydrothermal vents produced organic molecules like amino acids. These molecules assembled into complex, self-replicating structures, eventually leading to the first primitive life forms, prokaryotes. Around 3.8 billion years ago, the first living organisms appeared in these oceans. These were prokaryotes, extremely simple single-celled life forms with no nucleus. They didn't need oxygen to survive, because there was none in the atmosphere. Instead, they thrived in an anaerobic environment, using chemical reactions to obtain energy. Life at this stage was microscopic, but it marked one of the most important turning points in Earth's history. Then came a revolutionary upgrade. Some of these prokaryotes evolved into a special group called cyanobacteria. Unlike earlier life forms, they developed the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into energy. But here's the game-changing part. They released oxygen as a byproduct. At first, this oxygen didn't enter the atmosphere. Instead, it reacted with large amounts of dissolved iron in the oceans, forming iron oxide deposits known as banded iron formations. These layers are like geological evidence of oxygen slowly being produced and used up. Only after all this iron had reacted, basically when the oxygen storage in the oceans was full, did oxygen finally begin to escape into the atmosphere. This slow buildup of oxygen would eventually transform Earth forever, setting the stage for more complex oxygen-dependent life. So from tiny invisible cells in ancient oceans came the beginning of a breathable world. Around 2.4 billion years ago, Earth went through a massive transformation known as the Great Oxygenation Event. Thanks to photosynthetic organisms like cyanobacteria, oxygen had been slowly building up. But now it began to rise significantly in the atmosphere, completely altering Earth's chemistry. As oxygen accumulated, something incredible happened in the upper atmosphere. Some of it transformed into ozone, O3, forming the ozone layer. This layer acted like a protective shield, absorbing harmful ultraviolet UV radiation from the sun. Before this, intense UV rays constantly bombarded Earth's surface, making it extremely difficult for life to survive outside water. With this new protection and increasing oxygen levels, Earth became far more stable and life-friendly. For the first time, organisms could evolve that used oxygen for energy, which is far more efficient than anaerobic processes. This opened the door for more complex life forms to develop. Eventually, with UV radiation reduced and oxygen available, life began preparing for its next big step, moving from oceans to land. So this phase wasn't just about oxygen rising. It was about Earth becoming a safer, more advanced home for life to grow, evolve, and take over the planet. Imagine Earth wrapped in invisible layers, each one doing a specific job, like a perfectly designed shield system protecting life on the planet. From the ground we stand on, all the way to the edge of space, Earth's atmosphere is divided into 5 main layers, each more fascinating than the last. Troposphere, the life layer. This is where everything happens. Extending from the surface up to about 8 to 15 kilometers, the troposphere contains nearly 75% of the atmosphere's mass. It's rich in nitrogen, oxygen, and water vapor, making it the only layer where life can exist. All weather, clouds, rain, storms, occurs here. As you go higher, the temperature drops, which is why mountaintops are colder. This is literally our home layer. Stratosphere, the ozone shield above the troposphere. From about 15 kilometers to 50 kilometers, lies the stratosphere. This layer is calm and stable, which is why airplanes often fly here. Most importantly, it contains the ozone layer, which absorbs harmful ultraviolet UV radiation from the sun. Because of this absorption, temperature actually increases with height, opposite of the troposphere. Without this layer, life on Earth would be exposed to dangerous radiation. Mesosphere, the burning zone from 50 kilometers to 85 kilometers, is the mesosphere, the coldest layer of the atmosphere. Here, temperatures drop drastically as altitude increases. This is where meteors burn up when they enter Earth's atmosphere, creating the streaks of light we call shooting stars. It acts like a protective barrier, preventing most space debris from reaching the surface. Thermosphere, the energy zone, stretching from about 85 kilometers to 600 kilometers. The thermosphere is where things get intense. Temperatures can rise above 1000 degrees Celsius due to the absorption of high-energy radiation, like X-rays and UV rays. It contains the ionosphere, a region filled with charged particles that help in radio communication. This is also where beautiful auroras, northern and southern lights occur. Satellites and even the International Space Station orbit within this layer. Exosphere, the edge of space. This is the outermost layer, extending from around 600 kilometers to about 10,000 kilometers. The air here is extremely thin, so thin that particles rarely collide. It is mainly composed of hydrogen and helium. This layer gradually fades into outer space, marking the boundary where Earth's atmosphere ends and space begins. Thank you for watching this video, and stay tuned for part 3. If you enjoyed this, don't forget to like, share, and subscribe for more.